Okay, so here we're doing the deflection of a member, the elongation of member AB. We're trying to find the deflection of point B relative to point A, but since A is fixed, that's just the elongation of this member right here. Since it's tapered, we actually can't use the simple formula for elongation. So we're going to have to go back to our integral form. And if you remember that, that's the deflection is equal to um, the integral of P, or in this case, we're going to call it F since uh, that's the force. That's the internal force over A and E, and all of that with respect to X. Okay, so that's the generic formula right there, F dx over AE, the integral of that, right? Um, anything that's constant can actually be taken out of the integral sign. Since the only applied force is that guy, then the axial force inside the member is constant. Since it's all the same material, E is also constant, so I can actually simplify that to the integral of dx over a, let's see, let me take this outside. So this is going to be F divided by E times the integral of 1 over a dx, like that. And this is a is a function of x, right? So we got to be able to find out what that function is. Okay, so the first thing I'm going to do is write what we know up here. We know the diameter at A is 100 millimeters or 0.1 meters. We know the diameter B is 0.05 meters or 50 millimeters. We know the length is 2 meters, right? We also know that the force is 100 kilonewtons. So I'm going to write that as 100,000 newtons. So we're doing everything in meters and newtons. And I know that the Young's modulus is equal to 101. That's giga, so that's times 10 to the ninth. And that would be newtons per meter or pascals, right? So there's the known quantities right there. Next thing, I need this area as a function of x. Looking here, these look like straight lines, so it looks like the diameter is changing as a linear function of x. And we know that any linear function can be written as y of x is equal to mx plus b. So that's the slope times x plus the value of the function at x equals 0. So diameter of x is going to be the slope, which is the change in diameter, divided by the length, rise over run. So that's dB minus dA divided by the length L. So there's my slope. I'm going to multiply that by x plus the value of the diameter at x equals 0. That's dA. So there's my diameter as a function of x. The area then as a function of x is just equal to pi over 4 times that diameter squared. Okay, so all you need to do is write this function right down here. So delta is equal to f over e times, and we're going to do a definite integral here. That's going to go from 0 to L, and we're evaluating 1 over a of x with respect to x, like that. If I multiply that by 1,000, then that is my deflection in millimeters. So 0.504 millimeters is the final answer.